So we've just seen how comparator offset can be a real problem, potentially saturating the later stages of our pipeline ADC. This page shows us the clever solution. It's a technique called redundancy. Let's break down how it works. Take a look at the two graphs on the right. They both plot the residue voltage, VRES, which is the output of this stage, against the input voltage, VIN. The top graph shows a standard setup with no redundancy. In this case, for a 3-bit stage, where M equals 3, the residue voltage swings all the way from positive VREF to negative VREF. It uses the entire available range. But what's the danger in this? Well, if a comparator has a small offset and makes a decision that's slightly off, especially near those sharp peaks and valleys, the residue voltage can easily go beyond plus VREF or below VREF. When that happens, the next stage receives an out-of-range signal, it saturates, and we lose information. This is exactly what causes the missing levels and codes we saw on the previous slide. Now, let's focus on the bottom graph. This is where the solution is illustrated. This graph shows the same stage, but with redundancy added. The first thing you'll probably notice is that the residue voltage, VRES, doesn't swing as widely. It now only goes from plus VREF/2 down to VREF/2. We've essentially compressed the output voltage swing. How did we achieve this? The key is in changing the capacitor ratio in our ADC circuit. In the first, no redundancy case, the feedback capacitor CF is equal to the input unit capacitor CI. This gives the stage a gain of 2 ℧. However, in the second case with redundancy, we intentionally make the feedback capacitor twice as large, CF equals 2 CI. This simple change effectively halves the gain of the stage to approximately 2 ℧. By reducing the gain, we create an overlap between the different segments of the transfer curve. You can think of it as building in a safety margin. Now, if a comparator has some offset and makes a small error, the resulting residue voltage might be incorrect, but because of this compressed range, it will still fall safely within the plus or minus VREF input range of the next stage. The next stage can still process it, and this small error can be fixed later on by the digital correction logic. This technique is what gives the pipeline ADC its tolerance to comparator offsets. The final formula on the page quantifies this benefit. It tells us that by implementing this redundancy, the stage can tolerate comparator offsets up to plus or minus VREF/2 ℧. For our 3-bit example, this means it can handle an offset of VREF/8. This is a powerful and essential method for making our ADC designs much more robust and practical in the real world. So, we've seen how comparator offset can be a real problem, leading to missing codes. A very popular and elegant solution is what we see here, the 1.5-bit architecture. Now, the name 1.5-bit can be a little confusing. Does it mean we get half a bit of information? Not exactly. Think of it this way. For each of these stages, we get one effective bit of resolution for our final ADC output, but we use a 2-bit internal flash ADC and DAC to process the signal. That extra information gives us the redundancy we need to handle errors. Let's look at the diagram on the far left. A simple 1-bit stage would just have one comparison threshold, right at 0 volts. But here, in a 1.5-bit stage, we introduce 2 thresholds, one at positive V_EF/4 and another at negative V_EF/4. This creates a special offset correction range, highlighted in green. What this means is that our comparators don't have to be perfectly accurate. As long as their actual switching point, including any offset error, falls within this green shaded region, the digital correction logic down the line can fix the error, and the ADC will still produce the correct final output. This makes the design much more robust. Now, how does this actually work? Let's trace the operation on the V_out versus V_in graph on the bottom right. This graph shows the residue voltage, V_out, which is the amplified remainder that gets passed to the next stage in the pipeline. If our input signal, V_in, is small, somewhere between V_EF/4 and plus V_EF/4, the internal sub-ADC decides the signal is in the middle region. It outputs a digital code, in this case 01 foot, which corresponds to a K value of 0. The circuit then simply amplifies the input by a gain, which is typically 2. So, V_out equals 2 times V_. You can see this as the middle straight line passing through the origin. But what happens if V_ goes above plus V_/4? The sub-ADC detects this and outputs a different code, 11, which means K is plus 1. The circuit now does two things. It still multiplies V_ by 2, but it also subtracts a reference voltage, V_. This subtraction is crucial. It flips the output voltage back down, as you can see on the graph. This ensures the residue voltage stays within the valid input range for the next stage. Similarly, if V_ drops below V_/4, the code becomes 2000 foot, K becomes -1, and the circuit calculates 2 times V_ plus V_, pushing the residue back up into the valid range. The circuit diagram in the middle, called a flip-around topology, is a common switch capacitor implementation that achieves this exact behavior. The sub-ADC makes the decision and provides the digital bits, which then control the DAC portion to add or subtract the reference voltage as needed. The most important takeaway from this graph is that the sawtooth wave for the residue never has to reach the full reference voltage. The peaks are well within the plus or minus V_EF range. This overlap between the segments is the physical manifestation of our redundancy. It gives the next stage a much easier job and, as we said, makes the whole design tolerant to comparator offsets. This is a fundamental technique used in almost all modern high-speed pipelined ADCs. On the previous page, we looked at the flip-around topology for a 1.5-bit architecture. This page shows another popular implementation called the non-flip-around topology, which also cleverly solves the comparator offset problem. Let's first look at the diagram on the left. This shows us the core idea of the 1.5-bit stage. Instead of having just one comparator with a threshold at 0, we now have two comparators with thresholds set at positive VREF/4 and negative VREF/4. This creates three distinct regions for our input signal. The space between these two thresholds is our offset correction range. This range gives us some wiggle room or margin for the comparator's actual switching point to drift to offset without causing a catastrophic error. Now, how does the circuit in the center work? This is the non-flip-around implementation of the MDC. The input voltage, V_, is first evaluated by a sub-ADC. This sub-ADC contains the two comparators we just talked about. Based on which of the three regions V_ falls into, the sub-ADC outputs a 2-bit digital code, D1, which can be 00, 01, or 11. You can see in the small table that this digital code D1 is then mapped to a value K. If V_ is very low, below VREF/4, K is -1/2. If V_ is in the middle range, between VREF/4 and plus VREF/4, K is 0. And if V_ is high, above plus VREF/4, K is +1/2. This value K is then used to perform a digital-to-analog conversion. The circuit essentially subtracts a voltage of K times V_EF from the input signal V_. Then this difference is amplified. The formula for the output voltage, V_, tells us exactly this. It's the ratio of the capacitors, CS over CF, multiplied by the input voltage minus that reference voltage term, kV_. In this specific design, the feedback capacitor CF is half the sampling capacitor CS, so the gain, CS/CF, is 2. So the overall operation is, we compare the input, generate a K value, subtract kV_EF from the input, and then multiply the result by 2. This V_ becomes the input for the next stage in the pipeline. The graph on the bottom right beautifully visualizes this transfer function. As the input voltage V_ sweeps from negative to positive, the output V_ increases with a gain of 2. But once V_ crosses a threshold, like plus VREF/4, a reference voltage is subtracted, causing the output to suddenly drop down before it starts rising again. The same thing happens at 4F/4. The crucial part here is the overlap. Notice how the ramp sections overlap horizontally. This overlap is our redundancy. If a comparator's offset causes its threshold to shift slightly, say from plus VRF/4 to a little higher, the residue voltage V_out will still be within the valid range for the next stage to handle. The final digital value is corrected later, so no information is lost. This makes the entire ADC much more robust against component imperfections.